Hi, so in this video we will be discussing some of the initial papers of diffusion. Uh, they were basically introduced by this Denoising Diffusion Probabilistic Models (DDPM), us, and later on this is one seminal paper, Denoising Diffusion Implicit Models (DDIM), that made accelerated inference over DDPM. So let's discuss it. Let's go over it. I will go together with you. Uh, okay. So they present high quality image synthesis. Yeah, like before DDPM, people used to mostly rely on something like generative adversarial networks or VAEs to get good quality generations. But recently, almost everyone uses diffusion models. So let's see like how they work. So this is one of the initial papers, DDPM, on that. So we present high quality image synthesis results using diffusion probabilistic models, a class of latent variable models inspired by consideration of non-equilibrium thermodynamics. Okay, inspired by thermodynamics. It trains using weighted variational bound designed according to novel connection between diffusion probabilistic models and denoising score matching with Langevin dynamics. Okay, there is something like Langevin dynamics that we should be aware about, and then a progressive lossy decompression scheme that can be interpreted as generalization of autoregressive decoding. Okay, so these are some of the generations using celibate dataset uh, and unconditional CIFAR10 dataset here. So they are quite good quality at that time in 2020 when even GANs were there. These look like quite good quality, able to generate different types of objects, being able to model the diversity. Nice. Okay. And so there have been remarkable advances in energy-based modeling and score matching that have produced images comparable to GANs. Okay, so this has been done in VAs. Okay, so how does the diffusion model work? So, okay, so in this paper, what it does is that it takes an XT, which is a completely noisy image, and then gradually denoises it until we reach X0, which is the real looking image. Okay, so the background. Yeah, like we will be going over it step by step. So diffusion models are latent variable models of the form p theta x0. Okay, so it's taking a marginalization of x0 to xt over x1 to xt to get p of x0. So it's taking some joint distribution x0 to xt. Yeah, so this is one way of obtaining the real data distribution of x0. Now the issue is that uh, like can it be done in closed form? Okay, so p theta x0 to xt is called reverse process. So this thing x0 to xt, so here we go from sorry, x0 to t is called reverse process and it is defined as Markov chain with learned Gaussian transition pxt. Okay, so it's obtaining xt, uh, xt minus 1 given xt. This is the reverse process. So okay, so the reverse process is basically denoising process. p theta xt minus 1 to xt can be obtained like this. Okay. What distinguishes diffusion model from other types of latent variable models is that approximate posterior called forward process or diffusion process is fixed to a Markov chain that gradually adds Gaussian noise to data according to variance schedule beta 1 to beta t. Okay. Okay. So like in this diffusion model we gradually add noise using some schedule beta 1 to beta t, and then utilize those addition of noise. We somehow use some form of prediction to predict those noise that is added to each step. And the way the noise is added uh, in the forward process, which goes from a good looking image to noisy image, uh, it is added using some Markov chain that follows some that adds some Gaussian noise according to some schedule beta 1 to beta t. So this is the forward process. So forward process is xt generating noisier image from the previous less noisy image. Okay, so this is the posterior, and we know that the noise is added using this schedule where this is the mean and this is the variance. Okay, so this is the mean. uh I see. So it looks at the previous image xt minus 1, uh, and then samples something around 1 minus beta t times xt minus 1, and around that in the beta t region it samples something. So it's kind of like adding some form of noise. So this beta t seems like the extent of noise, I feel. Let's check. We will get to know later on. So training is performed by optimizing usual variational bound on negative log likelihood. Okay. Uh, so we are optimizing some variational bound. So like this is the ground truth distribution. So we are trying to maximize the log likelihood of the ground truth. Uh, and this can be seen as less than or equal to negative log of p theta x0 to t. Okay, so this is the for reverse process p theta x0 to t. Okay, and q x1 to xt given x0. I see. So this one is the forward process. So we are saying that this part is less than or equal to this part. Okay, I'm not sure how we got this. Hmm. Okay, then later on it can split pxt and then x0 to xt minus 1 given xt. Okay. Okay, so yeah, this seems like it is being decomposed like this, and then we uh, take this part out, and then keep we also take the product out to get this summation, and then we get this form. And I guess this one is same as this. Okay. Hmm. So this is interesting, like how to get this. Okay. Oh, this is a usual variational bound. So this is the joint distribution x0 to xt. Or held constant as hyperparameters. Okay, so beta t can be either learned or held as a constant for hyperparameters, and the expressiveness of the reverse process is ensured in part by the choice of the Gaussian conditional, because both processes have same functional form when beta t are small. It samples xt at an arbitrary time step t in a closed form using the notation. Okay. Okay, so if we use this particular notation, then we can sample an arbitrary xt given x0. So this is the forward process using this particular equation. So again, like it is sampling around x0, uh, around this particular part with this as the variance. Okay, so but isn't it reducing the mean? Like it is kind of, I mean, if I'm trying to interpret it, it's not sampling around x0, it is sampling around root alpha t of x0. Now alpha t is 1 minus beta t, and depending on the what we choose as beta t, I think beta t, if it is positive 0 to 1, then this thing will be small, so it will be smaller than x0. And let's say alpha 0 is 1 minus beta 0. Sorry, alpha 1 is 1 minus beta 1, and alpha 1 is alpha t bar is 1 minus alpha t bar. So this will be, if it is 1 minus sorry, alpha t bar for t is equal to 1 is 1 minus beta 1. So this will be beta 1 times I, beta 1 times I, and this will be 1 minus beta 1 root of 1 minus beta 1 times x0. Okay, so beta 1 is the, it is exactly like, okay, it's exactly like what we were discussing here. I see. But the again, like I'm not understanding why we are multiplying it with mean of alpha t, mean of square root of alpha t. Like why is this mean? So this is the question I have. Okay, so efficient training is therefore possible by optimizing random terms of L with stochastic. Okay, so this is L with stochastic gradient descent. Further improvements can come from variance reduction by rewriting L as, okay, if we rewrite L as this, Q of xt given x0 and P of xt and this part came from this part. Okay, I see. Okay, this is interesting. How did we get this whole part from this part? Hmm. So, what is scale divergence between these two terms? It is defined as minus qxt given x0 times log of qxt given x0 divided by pxt. Hmm. Okay, so this is interesting. Okay, we will look at it later on. We will see appendix A for details. Okay, the labels on the terms used in section 3. Okay. Equation 5 uses scale divergence to directly compare p theta xt minus 1 given xt against forward process posteriors, which are tractable when conditioned on x0. Okay, so this forward process is tractable when conditioned on x0. Okay. Yeah, this part is tractable. Now, what is this? Oh, okay. It is just expanding this part and this part. Uh, okay, so it's computing xt minus 1 given xt and x0. I see. So it is utilizing both x0 and xt to make to estimate xt minus 1. So all KL divergences in equation 5 are comparisons between Gaussians. So they can be calculated in a raw Blackwellized fashion with closed form expression instead of high variance Monte Carlo estimates. Okay, so it's saying Monte Carlo estimates have high variance. Uh, so it is instead trying to compute it using raw Blackwellized fashion. Okay. Okay, so let's see how many more papers we have, how many more pages we have to read. Okay, until experiments. One and a half, two and a half. Oh, just two and a half. Okay, almost 2 pages. So we are fine. We can do this. Okay, let's do this, man. Let's do this. So diffusion models and denoising autoencoders. So diffusion models might appear to be restricted class of latent variable models, but they allow a large number of degrees of freedom in implementation. One must choose the variances beta t of the forward process and the model architecture and Gaussian distribution parameterization of the reverse process. Okay, Gaussian distribution parameterization. But okay, so it's okay, so this is of the reverse process, that is the process of generating it. So like the parameters, the model parameters that we use to define Gaussian distribution to make the prediction, that obviously affects the quality of the generation. And yeah, what is beta t? That is again like something I have been trying to understand. And the model architecture and the Gaussian distribution parameterization. Okay, Yeah, model architecture obviously that also matters along with the parameterization. To guide our choices, we establish a new explicit connection between diffusion models and denoising score matching. So it is making some connection between denoising score matching and diffusion models that leads to simplified weighted variational bound objective for diffusion models. What is weighted variational bound objective? Interesting. We will come across it in next few steps. So ultimately our model design is justified by simplicity and empirical results, so which is in section 4. Our discussion is categorized by the terms of equation 5. Okay. Okay, so what is the forward process and LT? Okay, let's go over it. So we ignore the fact that the forward process variances beta t are learnable by reparameterization and instead fix them to constant. So it is now fixing beta t. Okay, it's not learning it. So yeah, this is interesting. Can it be even learn beta t? Because it seems to be the noise that we are adding. And now if we are even learning the noise that we are adding, then the model may be able to cheat, right? It may just do beta t equal to 0, and if we just learn them, then the model will just predict the same thing in every next step. Thus in our implementation, the approximate posterior queue has no learnable parameters, so LT is a constant during training and can be ignored. Okay, LT is constant. What is LT? Let me check. What is LT? Oh, this part. Oh, so computing xt given x0 and pxt, this thing is constant. I see. Yeah, like this thing should be Gaussian and this part is constant. Like it's not like there is no there is no variation in here, as we vary as there is no parameter to control xt given x0. It's like it's completely fixed, and this part is also fixed. So there is nothing to minimize here. That's the point. And what is the reverse process and L1 to t minus 1? Okay, so we discussed. So this is the reverse process. It is trying to produce the previous image given given the current noisier image. So it is trying to denoise, and it uses this to parameter to make the denoising of x t minus 1 given xt. So there is some time step t here, which is from 1 to t. So there are t time steps, right? Capital T. So for a given small t, it utilizes both the noisy image as well as the step, the counter. So this is the counter. In this, each one is a counter. So we, as the counter in goes down from capital T to 0, this thing predicts the real image. So first we set sigma theta xt comma t to, okay, sigma square I to untrained time dependent constants. Okay, so it is set to some untrained time dependent constants experimentally, both sigma t square and beta t and sigma t square, and is this had similar results. Oh, okay. So it is, this is the variance. It set it to sigma t square times I. Okay, and what is the sigma and how is it dependent over time? And it says that either we set this, okay, so it's something like beta ti, which is similar to this thing. So this did not help much. And the other is this part. So like I am not saying that this did not help much. I'm just saying that there was not much difference between setting it to this and this. Okay, the first choice is optimal for x0 is equal to this. Okay, so for this Gaussian noise, completely noisy image, if it is sampled from 0 to 1, sorry, it's sampled from standard distribution, then it's very then we can utilize this thing. Oh sorry, we can utilize this thing is optimal, and the second is optimal for x0 deterministically set to 1 point. Oh, it is even trying to set x0 to some single point. Interesting. These are the two extreme choices corresponding to upper and lower bounds on reverse process entropy for data and coordinate wise unit variance. Okay, so it's these are some extreme choices, it seems. I see. Okay, these are extreme choices. We have to again come to it. Okay, I think we will go over this paper again in the next video. That will be much more understandable for you guys, and I would be more eloquent in that. But for now, bear with me as I am trying to understand it. Okay, understanding the maths of DDPM. So, second, to represent the mean mu theta xt comma t, we propose a specific parameterization. Okay, so for this part, we propose a specific parameterization motivated by the following analysis of LT. So this is the LT. Okay. So p theta xt comma xt minus 1 given xt can be written as this, where everything is same and this has been replaced by sigma t square I. Then we can rewrite LT minus 1, which is the KL divergence between uh, the forward process x q of xt minus 1 given xt and x0 and p theta xt minus 1 given xt. This is the reverse process. We can write this in this particular form, where c is a constant that does not depend on theta. Okay, so we see that the most straightforward parameterization of mu theta is a model that predicts mu t, the forward process posterior mean. Okay, however, we can expand equation 8 further to reparameterizing equation 4 as this. Okay, we can further expand it using equation 4, this part. Oh, okay. If we use that, okay, I see. It's just reparameterizing xt given x0 and epsilon here as something like this, then we can like use this instead of this we can utilize this part, and then the forward posterior formula, that is this part. If we are applying this, okay, this will become a bit complex. Ha. I see. Yeah, so like once we get this form, and then we can further reduce it to this particular form by utilizing this particular equation. Okay, now the equation 10, okay, equation 10 reveals that mu theta must predict, okay, this part given xt, since xt is available as input to the model. uh, okay, yeah, like xt is the, for example, for a given point it is a noised version of the image, and we want to further denoise it to the next step. uh, so given that, the model must predict something like this, uh, this part. This is 1 upon root of alpha t times xt minus beta t upon 1 minus alpha t times epsilon. Okay, so now we may choose the, okay, since xt is available, so this is the parameterization. Okay, this part is same as this part, where yeah, okay, where epsilon theta is a function approximator intended to predict epsilon from xt. Okay, to sample xt minus 1 given xt minus 1 given xt is to compute xt minus 1 as this part, where epsilon is, okay, where z is sampled from Gaussian distribution with standard normal, so zero mean and standard deviation of identity matrix. The complete sampling procedure algorithm 2 resembles Langevin dynamics with epsilon theta as learned gradient of the data density. Okay, I'm facing some issues right now actually, not being able to understand it properly. So let me again try to uh, understand it. So what it is doing is that it's trying to use this particular uh, uh, like it is trying to reduce or optimize this particular aspect, and in this part we can expand the mu xt comma x0 as like this, uh, in the form of x0 and xt, and then we also utilize something like uh, x0 and xt, and then we also utilize 7 and 4. Okay, this part we utilized, and we also applied this part. Okay, So like the question I have is, what is the effect of beta, what is the effect of epsilon? I guess epsilon is just sampled based on beta, so it's fine. So it is dependent on beta. Mm. So again, like how is mu t xt comma x0 obtained? It is obtained like this, which is dependent on x0 and xt. Okay. Here like xt is replaced with xt is like this and x0 is obtained using xt. Okay. X0 is obtained using xt. Uh, Using this particular thing. And then we open this up mu t using this form. Okay, so we utilized this form and this form, okay, to get this part. And now uh, when we are trying to optimize this, we are trying to minimize this, so network is basically trying to predict this part. Mu theta has to predict this part, right? Yeah, mu theta must predict this part. Since xt is available as input to the model, we may choose the parameterization. Okay, this is the parameterization that we chose. Because xt is available, so we don't need to compute x, like we can obtain x0 from xt, I think. Now to sample xt minus 1 using this is to is like computing xt minus 1 from here, where epsilon theta is something that we use to compute epsilon, and then there is some sigma tz. Okay, okay, so this is the mean, this is the mean mu theta, and then there is also some other thing which is sigma. Yeah, beta t was sigma square, right? So I think that is the component. Okay, the complete sampling procedure algorithm to resembles Langevin dynamics. Okay, so we need to predict epsilon from xt, which is the noise that we add. With epsilon theta as learned gradient of the data density. Furthermore, with the parameterization 11, equation 10 simplifies to Okay, using this parameterization, equation 10 simplifies to, what is the equation 10? Okay, this part. It gets independent of xt. So it's like predicting epsilon theta given. So epsilon theta is predicting epsilon, which resembles denoising score matching over multiple noise scales indexed by T. Okay, T indexes the noise scale, the scale of the noise added, which is something like, which is kind of decided by beta T. Okay, I guess. As equation 12 is equal to one term of the variational bound of Langevin like reverse process, we see that optimizing the objective resembling denoising score matching is equivalent to using variational inference to fit finite time marginal of the sampling chain resembling Langevin dynamics. So it is saying something about Langevin dynamics. So to summarize, we can train the reverse process mean function approximator mu theta to predict mu t, or by modifying its parameterization we can train it to predict epsilon. Okay, okay, mu theta can be used to predict either mu t, or epsilon theta can be used to predict epsilon. Yeah, there is also a possibility of predicting x0, but we found this to lead to worse sample quality early in our experiments. Okay, we have shown that predict that epsilon prediction parameterization both resembles Langevin dynamics and simplifies the diffusion model's variational bound to an objective that resembles denoising score matching. Nonetheless, it is just another parameterization of p theta xt minus 1 given xt. So we verify its effectiveness in section 4 in the ablation, where we compare predicting epsilon against predicting mu t. Okay, so in section 4 they will be doing some discussion about which one is better, predicting either the mu mean directly or the epsilon. Okay, so we will read two more uh, some subsections, and then we are done for today. Okay, so data scaling reverse process decoder and L0. We assume that the image data consists of integers in 0 to 255 scaled linearly to -1 to 1. This ensures that the neural network reverse process operates on consistently scaled inputs starting from a standard. Aha! This is the reason. I guess this is the reason why we are multiplying everything with like root alpha t, because when we multiply with root alpha t, mean remains 0. Okay, so let me explain. So usually image data, the pixels, they consist of integers from 0 to 255. But when we are training this neural network using this data, uh, we usually use -1 to 1. This ensures that the neural network reverse process operates on consistently scaled input starting from standard normal prior pxt. This ensures that the neural network reverse process operates on consistently scaled input starting from the standard normal prior pxt. To obtain discrete log likelihood, we set the last term of reverse process to an independent discrete decoder. Reverse process is the generative process actually to an independent discrete decoder derived from Gaussian. Okay. Where D is the data dimensionality and I and the superscript I indicate the extraction of one coordinate. So it extracts one coordinate, then another, and it does it for each of the D dimensional data dimensionality. It takes the product to output this. It is using this direct delta function uh, because it wants to discretize this part. Okay. I don't know what is happening here. Okay, next. Let's continue. We can come to here in next videos. So simplified training objective. Now, okay, let's let's spend some more time here. What's happening, man? Those are data scaling, reverse process decoder, and algebra. Why is it even trying to obtain discrete log likelihood? Okay, simplified training objective. With the reverse process and decoder defined above, the variational bound consisting of terms derived from equation 12 and 13. Okay, 12 and 13 is clearly differentiable I see why we got px0 given x1. This is the reason, this L0. Now we wanted to obtain L0, which is x0 given x1. That's why we are doing this. Okay, so it's saying it's clearly differentiable with respect to theta, equation 12 and 13. However, we found it is beneficial to sample quality to train on the following variant of variational bound. Okay, so it's just training on this part. That's it. It's not considering this part and also not considering this part. I see. Huh. Where t is uniform between 1 to t, the t is equal to 1 corresponds to L0 with integral of discrete decoder definition, equation 13. Okay, for t is equal to 0. Approximated by Gaussian probability density function times bin width, ignoring sigma 1 square and edge effect. The t is equal to t more than 1 case correspond to unweighted combinations, unweighted version of equation 12. Okay, this part. Sorry. Hmm. Okay. LT does not appear because the forward process variance is beta TR fixed, so we don't use LT. This is the LT. Yeah, we don't use it. As we discussed, like we don't optimize this part. Since our simplified objective 14, okay, this is the training process. Since our simplified objective 14 discards the weighting in equation 12, it is weighted variational bound that emphasizes different aspects of reconstruction compared to standard variational bound. In particular, our diffusion process setup in section 4 causes simplified objective to downweigh Loess terms corresponding to small t. These terms train the network to denoise the data with very small amount of noise. So it is beneficial to downweigh them so that the network can focus on more difficult denoising tasks at larger t terms. We will see in our experiments that this reweighing leads to better sample quality. So it is saying that whatever weight it was adding here, when we remove this, it weighs it differently, this part, for different t's. And it is actually helpful because uh, uh, the smaller terms for smaller t, they train the network to denoise data with very small amount of noise. So smaller t correspond to smaller amount of noise. So it is beneficial to downweigh them so that the network can focus on the larger noise, which happens at larger t. Here, larger t means larger noise, less noise in t minus 1. Yeah, so that's all, folks, and I hope we can meet again in the next video to discuss next papers that are coming out day in case of diffusion models. And I know like there would be some questions, that there are some open questions that we still need to answer, and we will gradually answer them in the coming classes or coming videos. Thank you.